Welcome to next class, 8th. Okay, so we'll continue from the previous class regarding this beta alumina and Ag plus ionic conductors. Okay, superconductors. So the solid conductors, not super. It's solid and solid electrolytes. Okay, solid electrolytes. Okay, fine. So in the previous video, we learned regarding this brief introductory part of this beta alumina. So we'll go for next. The study of this solid electrolyte began from the year 1960. Okay, so with the discovery of high ionic conduction at room temperature. So what is that they had taken for this? It was your beta alumina. So in 1960 it started. So to where the high ionic conductivity was discovered, and in beta alumina and this rubidium. Okay, rubidium silver Ag4I5, something like that. Okay, so this is what combination they had taken, and they could find that there is more conduction was observed here in 1960. Okay, and this work was also done by Faraday. Okay, so Faraday in 1839 started 1839. Okay, he was the first Faraday who reported the high ionic conductivity at high temperature. Okay, so he worked on this lead fluoride and silver sulfide. Okay, so in this compound, so he worked Faraday, and he could find that at high temperature, this have high temperature work. So he could find that it's having the high conductivity, ionic conductivity, and from then it started. And in 1990, you can see the solid electrolytes was been studied much by Tauband, Tubanddt, Tauband. Okay, so in 1990, and he passed the direct current. Okay, he passed the direct current through the composite of silver iodide. Okay, silver. So in this composition, he passed this fellow, this scientist passed this direct current in this at around 100 degrees centigrade, and after the experiment he waved the electrode. He waved the electrode before and after the experiment. Okay, and experimentally, and he showed that electrode increase in weight. So there was in one electrode there was increase in weight. Okay, and the other there was decrease in weight. Okay, from the quantity of charge passed. So whatever the quantity of charge passed, so he could find that in one electrode, so there was increase in weight, and another electrode there was decrease in weight. So this was the experiment he found, and the current was carried by, so by which he thought that the current was carried by Ag plus. Okay, so that was his theory, so which transferred from one electrode to another electrode. Okay, migration through AgI, so this solution through AgI. So this was the theory put by the Tauband. Okay, so this is how. Now the conditions, if you see, what may be the conditions. Okay, so for a good solid electrolyte, okay, solid electrolyte, so the conditions are the large number of ions of one species should be mobile. So there should be large number of ions of either one species. Okay, a cation or anion. So you can see one species should be large in nature, so there should be large number. Okay, so the such type, this is required here. Okay, and the large value of n, if you take the conduction, that is sigma is equal to n e mu. So this is what we say. So here this n value should be more. Okay, that is a first condition for the solid electrolyte here. Okay, and second, if you see that there should be large number of empty sites for actually, if you see the structure, so like this, there should be large number of empty sites. So there should be large number of empty site. This is a requirement. Okay, so empty sites is required for the mobile ions to jump from one side to another side, like this. Okay, so this is the requirement for this. And if you see the third, the empty and occupied side should have same energy. Whatever the occupied side here and empty side, if you see here, so they should have same energy. This side should have same energy. This is important, they should have same energy. Okay, so if the energies are different, then the mobility of the ions may not take place. Okay, so same energy and lower activation energy should be there, then only the jumping of the neighboring sides can take place from one side to another side. This is what the this is what we can see, the third conditions is required. And the fourth condition, you can see the structure should be 3D. The structure, whatever the whatever this been there by this strong electrolyte, it should be in 3D structures. and with the open channels should be there, open channels. This is requirement, because why open channels? Because ion should flow from the channels, that is requirement, okay, through which the mobile ions should migrate. So that should be the main important here. And you can see the anions favorable should be polarizable, okay, whatever the anions which are favorable, they should be polarizable, okay. So this is what the this is what some of the factors which the solid electrolyte should obey, okay, should have. Okay, this is what. Now this beta alumina is there, this obey beta alumina obey all these four factors, okay, one two three four factors, and the fifth factor, whatever the polarization I said, anion should be the polarized. So this will this is not seen in beta alumina, okay. So beta alumina satisfies all above four factors here, four conditions, okay, but not fifth one, but Ag plus whatever is there, so it is going to satisfy the last one also, because of iodide, which is can be easily polarizable, so polarizable. So this is what you can see. Now if you come to beta alumina, so factors you came to know. Now beta alumina. So this beta alumina has a general formula M2O. This is what, okay, N times, that is X2O3. So this is what about when N is N ranges. So no, N ranges from 5 to 11. So this is what, okay. And M is a monovalent here. M whatever we are taking, it is a monovalent cation. M should be a monovalent cation. So it may be Cu plus or Ag plus, gallium plus, okay, or indium thallium plus, like this. And most of this you can alkali metals, okay, plus. So this should be the this or NH4 plus, H3O plus. These all M stands, okay. Here M stands for all these cations, okay. And finally X here. So this X stands, so X maybe your trivalent anions, that is like your Al plus 3, okay. So this is what, or Fe plus 3, Al plus 3, or Ga plus 3, gallium plus 3. So this is what about the X, okay. So the most now everything is over from this general formula. M should be this oxide, this is oxide. N should be in the range of 5 to 11. X is nothing but your this one trivalent ion. So this is what about the beta alumina, okay. Now the most important beta alumina which is mostly used is your sodium beta alumina, okay. So this you should remember, sodium beta alumina, this is mostly used, okay. So what is this sodium beta alumina? So M here, the name itself is taken as Na plus, that's why it is called sodium, okay. Sodium beta alumina. So here M is nothing but your Ma plus here, and X, because alumina is there, so Al plus 3. So this combination is taken in sodium beta alumina, okay. So usually they are taking in glass industry. So in the glass industry we are using this, okay. Oxides of Na2O is used here, which stabilizes this metal. So this is how they do here. Now the solid electrolyte began, this work was done by started by Yao and Kumar, Yao or Kumar, okay. Yao and Kumar, by in the Ford Motor Company. They started in 1966, okay. So this work, okay. And they found that when they were using this in this company, Ford Motor Company, Yao and Kumar, they found that the Na plus ions were very mobile at room temperature and above also, and they found that cation and they also found that the cations like cadmium ions, etc., example in ion extrinsically for Na plus, and these cations are two mobiles, okay. This is how they found not only the Na plus ions, but also they could find that some of the other cat ions like cadmium ions like this. So cadmium ions like this, they could also have the same mobility, okay, for as per Na plus ion. So this is what the Yo and Kammer found while they initially they in 19 in you say in 1960, they started this for 1966, they started this work. So this is what about the, I can say, the the movement of the beta alumina. So the work of the beta alumina started here. Now this beta alumina, if you see, the composition of this is somewhat 1A 1 plus X Na Al 11 O 17 like this. Okay, so this is one type of also plus x, something like x by 2 they give. Okay, and Na 1 plus x. Okay, this is the stoichiometric composition. Aluminum will be there, AlX. Okay, or some Mg they are going to take. I will write here Na 1 plus x. Magnesium will be there. Okay, then x, then Al, you can see here minus x, oxygen 17. So like this. Okay, so this is your beta alumina, this is your beta double dash, like this. There are two types of beta alumina is seen here, one beta double dash and beta alumina. You can see Na 1 plus x, aluminum, oxygen oxides will be there of this particular. Don't bother about this is stoichiometric ratio here, because they are not very complex structure. Okay, not like simple structure like NaCl, rock salt structure. So here same thing here, magnesium is there. So when magnesium is doped here in this composition, so you can see here that is called beta double dash. Okay, so this is how you can see the beta alumina is, which is found in beta and beta dash, two types. Okay, and good sodium ion conductor at moderate temperature. You can see this beta alumina, they act as a good ion conductor here. Okay, and here beta double dash, okay, this one magnesium, so this is stabilized by addition of lithium plus or magnesium plus to, like here. Okay, so they are stabilized by addition of lithium sometimes and magnesium plus 2. So this is how. Okay, so this is the difference between beta and beta dash here. And if you see if the x value here, so from the, as I said, the general formula M to O or N I have shown in previous year, N Al to O3. In from the general formula, if this x or n, or you, I will take it as x, if it ranges from 5 to 11, 5 to 11, then it's a beta. Okay, if the x value ranges from the 8 beta dash, 5 to 7, it is beta double dash. If it is from 8 to 11, that is gives beta material. Okay, so you should remember this. If this stands from 8 to 11, that is beta material. If this x stands ranges from 5 to 11, then it is beta double dash. This is a difference between the beta and beta dash. Okay, and even the arrangement also. So this beta alumina, so it is made up of blocks like this, 1 2 3. Okay, like this. These are all SB they will mentioned here, and it has been proper A B C A B C A B C A B C, like this, properly arranged here. And you can see here there are two like this. Okay, so this is how it is been measured here. So this is given by C from here. Okay, and this is your beta dash. And if you see beta, same thing will be there here, same spinel block here, 1 2 3. Okay, this all SB, and here same thing here, you can see small and big. Okay, but here this is a mirror image. Sometimes this is a mirror image. Okay, see mirror plane, I can write here mirror plane from here. Okay, so here, so this is your beta. Okay, so that is difference, but this stack is very complex, so it's not like here arranged correctly A B C A B C, somewhat A B A C C B B C again A B A C, like this something. Okay, so this is not properly, it's very complex. Okay, so beta, so this is more complex. Okay, here 10 layer sequence is found here. So in beta, so 10 layer sequence, 10 layer sequence, okay, in is found here. Okay, and what is this small here? So this small is nothing but your Na plus ion. The small stands for here Na plus ion, small hole, and the big hole stands for oxide. This is a oxide layer, oxide. Okay, and what is this SB? SB means the spinel block. SB, it is a spinel block. So this is how the beta alumina, beta and beta double dash is made up of. Okay, so it is a closely oxide packing here, is going to found here in beta and beta dash. So this is a block study, and even if you see the conduction here, so they are made up of something in this plane, 1 2. So we will go for this plane, like this it is. Okay, so some gaps and this will be there, and you can see this is how it will be. I will take it here, 1 1 2 3 4. So we'll increase here. Okay, so ABR 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 ABR. Okay, this is one plane like this. okay, ABR, and in between you can see there will be M, BR, M, BR, M, BR, M, BR, like this. Okay, so like this it will be, and then this is a plane like this on this 3D structure like this. Conduction plane, this is a conduction place like this. Okay, so this is how the conduction plane will be there, and in this is a plane here, ABR, 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 and this is, so what is this, this is M is small m is standing here, so it is nothing but mid oxide position. M stands for mid oxide position. Okay, so M stands for mid oxide position. Okay, and what is this BR? Beaver's Ross side, Beaver's Ross side, Beaver's Ross side, and ABR is what? ABR is nothing but your anti-Beaver's Ross side, anti-Beaver's Ross side. So this is how it is been mentioned here. M is mid oxide positions. This in between it will be there mid oxide positions like this, M, and BR in between will be there always. So that BR is the Beaver's Ross side, and ABR is nothing but plane where the movement will be there of the ion, that is called anti-Beaver's Ross site. Okay, this is how it is. This will be made up of, okay, beta alumina. And if you see the conduction mechanism here in this beta alumina, the conduction mechanism, actually the BR, ABR, and M sides form a hexagonal network here like this. Okay, so these three sides, they form a hexagonal network here, and for a long range migration to occupy, an Na plus ion must pass through. Now Na plus ion must pass through, how far? To get a long range migration, they have to pass through like this, that is your ABRM, ABRM, BRM, like this is a sequence. Okay, so they should pass in this way, ABRM, ABRM, BRM, like this. So this is a sequence the ion should pass. Okay, most pass through the sites in the sequence, and the activation energy for the conduction is around 1.16 electron volt. Okay, very less. Okay, and represents small value here of migration of Na plus ion from one BR side to next BR side. Okay, so this is what we can show here. Okay, of the beta alumina here. Now if you see the beta dash alumina, some here one more thing you have to keep in mind is beta dash, okay, alumina. So they will ask in the examination, very important. So it is as I said now previously, it is made up of the close packed layers, okay, of oxide ions, and it is stacked in 3D dimensions, stacked in STACKED, stacked in 3D dimensions. Okay, 3D, but only the fifth layer, important here, fifth layer has three quarters of its oxygen missing. So that in the fifth layer there is oxygen missing. Okay, and you can see the Na plus ion reside. So here only wherever the oxide missing, the Na plus ions, so okay, they reside into this deficient oxide deficient, they reside into this oxide deficient layers here. So Na plus will reside in this oxide deficient layers, and they move easily. Okay, and why they move easily here in this? Because of the two reasons. That the first reason is that there are more sites available for Na plus ions to occupy. There are more sites available for Na plus to occupy that sites here, which has the oxides oxides is missing there. And the second is the radii. So if you take the radii, radius of Na plus is less than O minus 2. Okay, so radius of Na plus is less than O minus 2, oxide, and therefore it can easily pass. Na plus can easily pass very nicely. It will be movement will be there here. Okay, so this is how we can say. And this radius, yeah, that's what. And both here, the beta and beta dash structures are related to spinels. Both beta and beta dash structures are related to spinels. They are related to spinels group. Okay, we will learn this also. So here, and this is what about the beta alumina. One thing you can keep in the mind. So 5 stacks, 1 2 3 4, we will take like this, 1 2 3 4 second, 1 2 3 4 5 third, 1 2 3 4, 1 2 3 4 5. Yes, see here, like this. So 1 2 3 4 5. Now you can see like this. Okay, yeah, I will take in this way. Now you can see here. So in the fifth layer, every fifth layer, 1 2 3 4 fifth layer, there is a conduction band. See, So there is a gap here like this, there where the oxide is missing here, the oxide is missing here. So there is a large channel here, and in this channel only Na plus ions can move easily, Na plus ions can move easily, and that will help for your conduction. The fifth layer, conduction plane, this fifth layer is called your conduction plane. In previous we have shown, no, like this, ABR, ABRE, this is our plane. Okay, so ABR, ABR in the last this one we have shown you that in the previous, let just we have diagram we draw 3D dimension. So this is how we can explain regarding this beta alumina. Okay, now this beta alumina is 2D, I can say, conductors. Okay, alkali metals ions are freely within this conductor. So alkali metal ions move freely within this conductor planes, but cannot penetrate here, but they cannot penetrate the spinel blocks, as I said here, SB. So they can move, but they cannot penetrate the spinel blocks, dense spinel blocks. Okay, and the conductivity of the ion is exchanged. Okay, exchanged beta alumina is highest here. Okay, the conductivity of ions exchanged, okay, is the highest here in beta alumina, very fast they can have, and they have the very lowest activation energy. That is important. Activation energy is very lowest for Na plus usually and Ag plus. Okay, but if you increase the cation size, like for example K plus or thallium plus, okay, if you increase the size, then it cannot move mobile. Okay, it cannot move through the channels very nicely, and what happens, the conduction decreases. So this also you have to keep in the mind. For example, if you take lithium plus, again problem, beta alumina. So if you dope this lithium plus beta alumina, then it is not good. Okay, because it is having high activation energy and low conductivity. This having low conductivity. Why? Because lithium is very small in size, and compared to Na plus and Ag plus, and this small polarizing cation, this is a polarizing cation, and it is not happy in the large area. So lithium is not happy in the large area because it's a highly polarizing cation, and that's why this is not going to be good conductor. So lithium is not good. So this is how we can say. And the conductivity data for beta alumina, it fit no, in the equation of the long range temperature up to 1000 degree conduction. Okay, it fit into this Arrhenius theory Arrhenius equation for a long range of temperature up to 1000 degree. Okay, whereas NaCl, we have seen that in contrast to NaCl, it is around 300 or something 8 degree centigrade, some very less. So here it is long range. Okay, beta alumina. And if you see the NaCl simple structure is there in NaCl rock salt structure, but the conduction is very complex in NaCl. The conduction is very complex in NaCl, while in beta alumina you can see, though it is very complex structure, 3D 2D structures, but the conduction is very simple. You need no any nothing is there here. Conduction is very simple because of free movement of the ions will be there. So this is what about the beta alumina here. Okay, and even the sigma value is independent here, so it is reproducible also. Whatever the sigma value, conduction value we get in beta alumina, it is reproducible. Okay, so anywhere you go, it can be reproducible, same amount of sigma value we are going to get. And they are insensitive to small amount of impurities. They are also insensitive to impurities, small amount of impurities. But in NaCl we have seen how much problem is there of the impurity effect. So we had written, but here there is no need of impurity here, so it is free from impurity. So we know it's a very good conductor just because of the flow. Much larger amount of mobile ions will be there, and conduction is going to take place here. Okay, and even the activation energy, I said, very less, 0.16 electron volt. This is what, and n value is very large in beta alumina, and this is what I can say of the beta alumina. And if you see the one more last finally graph, if you want to show, I will show here like this. So this is conductivity of single crystal beta and beta dash alumina. Okay, if you see here, so you take this as a log sigma to the temperature per ohms per centimeter Kelvin, and this is your temperature inverse 1000 Kelvin per T. Okay, so you can see here 2 4 6 8 10. So here you can take 5 bar, 4 bar, 3 bar, 2 bar, 1 bar, 0 1 2 3, something like that. So here you take 300, some 0 minus 100 minus 150, something like that. Okay, so this if you take the graph here, okay, so if you see, so you can see like this, something like this. like this. Okay, if you see this, this is your sodium beta, this one NAB, beta sodium, this is silver, this one is your silver beta alumina, and this whatever 300 degree it is having diversion here from 300 high and coming here and having here, so this is your beta dash. Okay, so this is your sodium beta dash, and this one lowest, you can see this is your potassium beta, and this one is your thallium beta, thallium beta. Okay, now you can see here from this graph, you can see here the conductivity of beta 2, only one I will say tell you here. From 300 you can see the conductivity of beta 2 here. Okay, so what you are observing here is several times highest here than beta. So this is a beta 1 2, but here you can see conductivity is several times higher. It starts from here, both here, but conduct here from beta it is starting from somewhat like this. So here conductivity is highest, beta 2. Okay, so highest than several times highest than the beta form. Okay, at 300 degree centigrade. This is your 300 at 300 degree, at 300 degree centigrade. Okay, while when the temperature is operative of if you say sodium sulfur cell, so this is not required. So this is how one example we can see here, how it varies here of different. So it's here your conductivity is very less for you can see the potassium beta alumina and thallium beta, very low. This is having very highest here, but for beta 2 it's tremendous here at 300 degree. Usually it is showing several times higher than these two. Okay, so this is what from this graph we can observe the change. Okay, so I think this is more than sufficient for today's video. So in today's video almost we have learned regarding the beta alumina. Okay, beta usually forming in two structure, that is beta and beta double dash. Okay, so this is what we learned today, and probably I think in beta alumina we are totally completed, so not much to be learned now here in beta alumina. In the next class we'll go for silver iodide. Okay, silver plus solid electrolyte, so that will complete your these two concept as a part 3. We'll learn this. Okay, thank you.